Hello guys, this is Vishnu, and today, I mean, my physics concept video topic is normalization. It's from quantum mechanics chapter. So let's get started. So, what basically is a wave function? So, a wave function is something which describes mathematically about a wave or of the quantum state of an isolated quantum system. So, a wave equation would help us to recognize or not recognize, but the probability of finding a particle in a particular location. So, for example, for finding electrons, which are fermions, Y fermions, it um, follows or supports the Pauli's exclusion principle, and the photons or bosons. Bosons, in bosons, one of them is photons, and fermions, one of them is electrons. So bosons are nothing but bosons. It's Bose and Einstein's principle. So theory, I guess. This is all about it, and these are fermions and bosons, the photons. So Schrodinger wave equation. So let's see his wave equation. This is minus h bar by 2m plus partial derivative square of the wave function by the partial derivative with respect to the x, 2 times partial derivative of the wave function with respect to x, and plus v times the wave function, which is equals to I times, which is nothing but the complex number, I times h bar partial derivative of wave function with respect to time. This is an equation when it is when we are considering with space and time. X is nothing but the distance and time, we can say. Distance and time. So this is the Schrodinger equation, and we can reduce it to um, h bar square k square by 2m plus v naught, which is equals to h bar w, which we can also write it as square by 2m plus v naught is equals to e, where um, this is not p, but it's something phi square by 2m. This represents the kinetic energy. This represents the kinetic energy, and this represents the potential energy. And we all know that kinetic energy plus potential energy is nothing but the total energy. So, moving on, as you can see, we cannot utilize this function right away because there is a complex number which is present, and we cannot uh, uh, we cannot use it directly, and mm, this function doesn't even represent the actual wave function. So it's not even close enough, but it's a equation which is derived by Schrodinger, and it does follow. So let's move on. So normalization, basic normalization condition is it should be of integral of infinite minus infinity to plus infinity. Um, Wave function, since we are going with space and time, it's x comma t multiplied by complex conjugate of x comma t. We will see it later. What is a partial conjugate? Dx should be equals to 1 always. So this is the condition. And let's consider wave function. This is an example. Let phi of x comma t be equals to, um, let's consider one, a e to the power minus, okay, plus I kx minus omega t. So let's consider this wave function, wave equation, sorry, and its complex conjugate would be the minus power. We will see that x comma t is equals to a e to the power minus I of kx minus omega t. This is the partial, I mean, sorry, complex conjugate. So moving on, we can solve it with two methods. So this is method one, uh, by simply using the integration. So let's consider limits a b, normalizing it. So 5 times of a complex conjugate should be, okay, sorry, it should be dx 1, uh, which is equals to, in my case, a b, uh, 5, we know that a e to the power I kx minus omega t times of a e to the power minus kx minus omega t, dx should be equals to 1, should be equals to 1. So which should again be equals to, we can multiply a and a, which is a square. We can take it out from the integral, and since the base of e and e, I mean bases are same, e, so we can add the powers. So integral of a b, e to the power I into k x minus omega t minus of I into k x minus omega t, and we can plus minus cancel out each other. Dx should be equals to 1, which should be equals to a square of ab 1 dx equals to 1, and integral of 1 is x, so it would be equals to a square times of x ab should be equals to 1, which is equals to a square times of b minus a, which is equals to 1, which is equals to a square equals to 1 by b minus a, which is equals to a is equals to 1 by square root of b minus a. And we just found out the a value, and the actual wave function, I mean the wave equation would be this: phi is equals to 1 by root over of b minus a, times of e to the power I into kx minus omega t. So this is a wave equation, right? So this is a wave equation. So method 2 is different. It it would be utilizing the cos and sine functionality of the complex numbers. So since we know it's, but the normalization would be same. So phi would be equals to a e to the power I into kx minus omega t, which would be equals to, it's not z, it's equals to um, a into cos of kx minus omega t plus I sine of kx minus omega t. And similarly, function equals to a into e to the power minus I times of k x minus omega t, which is the complex conjugate, which is equals to a times of cos of kx minus omega t minus I sine of kx minus omega t. And after multiplying these both, we would get a squared times of, I'm directly writing it, a to b phi times of complex conjugate of phi uh, dx would be equals to uh, a square times of, since this is a, this is in the form of a plus b, and this is in the form of a minus b, and we know that since a plus b into a minus b would be equals to a square minus b square, and we know that I square equals to minus 1, and with the help of these we can say that it would be uh, cos square kx minus omega t plus sine square kx minus omega t, and with the help of the trigonometric equation we know that it's a square times of 1, anything of the degree of angle, cos square theta plus sine square theta equals to 1, and it's a square equals to 1, and this would be a b phi x, sorry, it's phi into phi times of complex conjugate of phi is equals to 1, which is equals to a b of a square dx dx equals to 1, which is equals to 1 dx, and a square times of x of b a is equals to 1, which is equals to um, a is equals to similarly 1 by root over b minus a. And this is the second method, and this is a problem. Determine the value of a such that the following wave function wave equation e to the power I n x function is normalized form from 0 to 2 pi. So limits have been provided for us. So the given wave is um, this in terms of xt only, a e to the power I n x, which should be equals so, and the complex conjugate would be a e to the power minus I n x, a e to the power minus I n x. This is the complex conjugate, and let's go with method one, which is AB 5 times of complex conjugate equals to dx equals to 1 equals to 1, and which should be equals to 5 times of 5x dx equals to 1, and a e to the power I n x, limits are given. A is 0 and b is 2 pi, so 0 to 2 pi limit. Phi is nothing but a into e to the power I n x times of a into e to the power minus I n x. This is also similar fashion, similar way we will be dealing with. We'll be multiplying the a, and which would be, it would be a square, sorry, can, but I don't want to, and a square times of 0 to 2 pi, 0 to 2 pi e to the power inx e to the power minus inx. Since the base is common, we can add the powers. Inx minus inx dx should be equals to 1. It's like only equals to 1, and it would be a square times of x, b, instead of ba, let's go with the pi, 2 pi and 0, which would be 2 pi 0 equals to 1, which is equals to a square times of 2 pi minus 0 equals to 1, which is equals to a square equals to 1 by 2 pi, which is equals to a is equals to 1 by root over 2 pi. So with the help of this, we found out the a value, and now let's write the wave equation, which is phi is equals to 1 by root over 2 pi, 1 by root over 2 pi times of e to the power I n x. Hence, this is our normalized form. This is normalized, and yeah, that's it. And thank you.